All right, PCH, we have evaluated limits from graphs. We have evaluated limits from tables. Now, today we're going to talk about evaluating limits algebraically, when we just are given the function and we do not have a graph or a table, and we're not able to come up with those things on our own. And so there will be a lot of algebra that we do in this lesson. It will be long, so do your best to stay with me. Pause when you need to, and come ready to class with any questions that you have. All right. In order to get ready for this lesson, it's really important for us that we know how to factor. And so I've given us an example here. I'm going to go through it with you together. I feel confident that we can factor any expression that has an a value, like this coefficient in front of my squared term, that is 1. But I do want to go over an example where the a value is not 1, because that changes things just a little bit for us. And so when that is the case, we notice that, hey, our a value is 2. The first thing we want to do is multiply my a value times my c value. In this case, 2 times 5 is going to be 10. And so when we're looking for our two factors, or well, not factors, but our two numbers that we're going to use to split our middle term, we are looking for factors, in this case, of a times c, factors of 10, that add to my b value, so that add to 11. And it looks like those numbers are going to be positive 10 and positive 1. Is that when we get those, we're going to throw this into an area model, keeping our 2x squared, throwing that in the top left box, my positive 5 in the bottom right box, and then using our two other boxes to, again, split this 11x, my middle term, into 10x and positive 1x coming from here. What this allows us to do then, of course, is to pull out our GCFs of each row and column. If I'm looking at this first column, 2x squared and x, both of those share an x in common, whereas if we're looking like at this first row, both of those terms share a 2x in common. You'll go ahead and do the same thing for the rest. On this bottom row, 1x and 5, those don't share anything in common, so we're just going to pull out a 1. And then in my last row, those both share a positive 5, so that our factors are 2x plus 1 and x plus 5. And there we go. We have factored this quadratic. Now, I know some of us, we don't really like using the area model and plugging this into this box and then pulling the GCF out that way to get our factors. And so I went ahead and over here on the right in black, some of you just like to rewrite it out just like line by line. And I wanted to show you what that looks like as well for those of you that feel more comfortable doing this option on the right. You end up getting the same factors, of course, because you're doing the same process. It just looks a little bit different. So that is there for you as well. When we're looking at trying to evaluate limits algebraically, we're going to do a couple of things in a specific order. A lot of the times, and one of the most beautiful things that's going to be like the case for us is when we are given, as we're looking down in these examples, right, we don't have a graph, we don't have a table, we're given the limit as x approaches 2, like in example A, of a function. They're actually going to list it out. It's not just going to be f of x or g of x, but that's actually going to give us the function. And a lot of times, this is going to be on a no-calc portion of the exam where you're not going to be able to graph this and try and evaluate it. You're not going to be able to use your graphing calculator to come up with a table. And so that's why this evaluating limits is going to be really key when we're doing it algebraically, because the majority of the time, I'd say like almost all of the time, this is how you're going to be evaluating limits on the AP exam. And again, it's going to be on the no-calc portion, so you won't be able to use a graphing calculator to help you out in another way. And so when we do this, our first thing we always want to try is direct substitution. We'll get to some of these other steps, and you'll see like in number 3, the reason we did factoring in our warm-up is because one thing we might need to do if direct substitution doesn't work is to factor, and we'll see examples of that in a little bit. But in this first table, A through F, I'm telling you, we just get to use direct substitution. What that means is simply, if we're trying to evaluate the limit as x approaches 2, we're just going to be plugging in 2 in for x anytime we see it in this function. And so when I do that, 3 times 2 squared minus 5 times 2 plus 4 we are going to get that this limit equals, and I'll go ahead and write that up here actually. Well, 2 squared is 4 times 3 is 12 minus 10 plus 4. Looks like that's going to be a positive 6, and this would be the y value that this graph is approaching as we approach an x value of 2. Letter B is going to be very similar, so I went ahead and just did it already, showed my work. I feel very confident that you could do this on your own as well. When you substitute an x value of 2 into this function, you end up getting the limit as x approaches 2 of this function equals 3. But what I want us to really focus on these next few minutes is when we look at examples C, D, E, and F, we have a bunch of different functions. We have like a natural log in letter C. We have radicals in D. We have a trig function in E, and we have a log in F. These are all functions that we have talked about all throughout this year, and there's a reason. Again, these questions, evaluating these limits, you're not going to have a calculator to be able to do this. And when you when you substitute in these x values into these functions, you're going to need to know how to evaluate each of these different functions. And they're going to look a little bit different. For example, if I'm looking at letter C and I'm plugging in the number e, right, because e is a number, into this function, I get the natural log of e over 3 times e. For us, we need to know, right, you should know that the natural log of e is equal to 1. Because the natural log has a base of e to what power equals e? Well, e to the first power equals e, and that's why the natural log of e is 1. We've talked about that. You've seen that before. AP Calc expects you to know that, and you will not have a calculator to figure that out. Divided by 3e, and of course, this is what you'd see as an answer choice on the multiple choice section. They would not expect you to multiply 3 times e, which is 2 point, whatever, 1 divided by that and get some decimal. This is going to be your final exact answer. But you needed to know that the natural log of e is 1. Same thing, I'm going to go ahead and skip down to letter E. If I'm looking at plugging in pi over 6 into this function, well, I'm going to get sine of 2 times pi over 6, so I'm going to get 2 pi over 6. That just means I'm evaluating sine of pi over 3. Again, you won't have a calculator to do this. You need to know how to evaluate the sine of pi over 3, and that's why we talked about it so much this year. And when I got back, I talked to you about this trick that we can use using our hand. And so I want you to tell me sine of pi over 3. Let's do it. Yes, when you evaluate the sine of pi over 3, you will get square root of 3 over 2. And it's going to be positive, of course, because any trig function, including sine, is going to be positive in the first quadrant, which is where this angle of pi over 3 resides in our unit circle. Again, that's something you will need to be able to do in AP Calc. Let's go ahead and go through D and F together just quickly. If I'm substituting 4 in for x here, I get the cubed root of 4 plus 4, which is the cubed root of 8. And you should be able to evaluate that and say, hey, the cubed root of 8 is 2. And that is my limit for D. Letter F, we plug in 5 in for x. We have the log base 3 of 5 plus 4. I'm just going to go ahead and say, hey, 5 plus 4, that equals 9. We need to know how to evaluate logs as well. Oh my goodness. It's a good thing we practice this a lot. In December, in Unit 4, we said, hey, if we're trying to evaluate a log, and this is equal to something, well, we talked about this as the chubby hand rule. 3, my base, to what power equals 9? Well, that's going to be 3 to the second power. 3 squared equals 9. And so this limit is 2 as well. All right, let's go ahead and move on to another example. And again, our first instinct, the first thing we want to try and do is direct substitution. So when I'm substituting 2 in for x, I get 2 squared, so 4, plus 2 minus 6, all over 2 squared minus 12 plus 8. And when I'm evaluating this, right, 4 plus 2 is 6, minus 6 is 0. That's, fine. That's what it is. But I notice that when I evaluate in my denominator, I get 4 minus 12, which is negative 8, plus 8. That also equals 0. And that is a big, big problem for us. As we know, we can never divide by 0. That is an issue. And so you might be tempted to say, hey, we're dividing by 0. I'm just going to say this limit does not exist, and I'm going to move on and live my life. Well, unfortunately, with limits, when you get to a spot like this, when you're evaluating algebraically, you are never done. Rarely, if ever, are you going to be evaluating a limit algebraically for AP that's going to be does not exist. There's always going to be some other step that you can do to rewrite what you have in a way that's actually going to be able to let you evaluate it. And so I do want to point out that I have the graph of this function over here on the left, and you'll notice that at an x value of positive 2, we have something going on here. While the function value might be undefined, right, because we have a hole here at the graph, and we'll kind of walk through this as well to see how we can determine this algebraically when we don't have a graph. We've talked about already in the first few lessons. Just because our function is undefined at some x value, that does not automatically mean that the limit doesn't exist. And we can see that in this graph. And so this is like, I'm using the graph to show you, hey, there's a reason why we can't give up if we were to come to this place and try and assume that the limit does not exist. That's not true. And we see that looking at the graph. But we need to know, hey, even if we're not given the graph, we still cannot give up. And so when this is the case, we need to go back up and try something different. If I'm looking at the list of things that we have done, right, we tried direct substitution, and it did not work for us. So we need to go to our next step. The principal limit theorem, that's really focused on limit from the left and limit from the right. You don't use that super often, so we're just going to skip over that one. And our next thing that we are going to want to try is to factor. We want to see if once we factor, is anything canceling out? Is anything changing? Like what is happening? Because that's going to help us in a way that you will see here in a second. So I'm going to go ahead and erase this, and we're going to factor. If I'm looking at my numerator, looking for two numbers that multiply to negative 6, add to positive 1, looks like that's going to be a 3 and a negative 2. And so my factors in my numerator, I'll go ahead and write this using proper notation. The limit as x approaches 2 of x plus 3 times x minus 2. Again, feel confident we can do this on our own. Same thing with the denominator. When I factor that, I'm going to get factors of, it looks like, x minus 4 times x minus 2. Add to negative 6, multiply to positive 8. And oh my goodness, what do I notice when I'm looking at my function in factored form? I have a factor in my numerator that is canceling with a factor in my denominator. And we know, based on what we talked about in Unit 2 earlier this year of PCH, is that when I have this happening, factor in my numerator canceling out with a factor in my denominator, that is when I have a hole on my graph. And of course, we already talked about it. That is what's happening at x equals 2 on my graph. Excellent. So that makes sense to us. So when I'm saying here, hey, a lot of times on AP, there's a reason that they're asking you about the limit as x approaches some value, usually because there's something fancy going on there. And in this case, we know that at x equals 2, there is a hole on this graph. When that is the case, when I have these factors canceling out, I'm going to go back to direct substitution, right? Once we find a step here that works, we found, hey, direct substitution didn't work at first, but once we factored, yay, that was good for us. We're going to go back always to direct substitution with my simplified function. And so now I have the limit as x approaches 2 of x plus 3 over x minus 4. When I do my direct substitution, I'm going to get 2 plus 3 over 2 minus 4. 2 plus 3 is 5 over 2 minus 4 is negative 2. And that is going to be my limit. So I can even put that back up here for my original limit, 5 over negative 2. And something we see when we look at the graph is, like, that is where my hole is at, to negative 5 over 2, which is negative 2.5. And we see that is the case. And in all honesty, none of what I did here should be new to us. When we were talking about holes in Unit 2, which was way back in Try 1, we said, when I'm asking you for where the hole is a point on my graph. I can't just tell you what the x value is. I also need a y value. It needs to be a coordinate point. In order to find the y value, I plugged in my x into my simplified function. That is exactly what we did here to find my y value. And so, while we are doing calculus and while we are evaluating a limit, which is something we haven't done before, all of the actual math we're doing, all of the algebra, none of that is new to us because we've already talked about it. We've already learned it, which is really, really nice. I want you to recognize that. This is going to feel like a lot, but you know how to do all of this stuff. Honestly, the biggest part that might be a little new is connecting it conceptually to what we're talking about in terms of AP calculus. So let's go ahead and try a second example. All right. When I'm looking at letter B, I notice that the function I have is the exact same. This rational x squared plus x minus 6 over x squared minus 6x plus 8. The exact same rational that we were working with in letter A, but we notice this time we're looking at the limit as x approaches 4 from the right. We're looking at our limit as x approaches a different y value. And so I'm going to try this again. I'm going to start with step number 1, which is direct substitution. And when I plug in a 4 into my numerator, I get 4 squared, which is 16, plus 4 is 20, minus 6 is 14. All right, all right, all right. My denominator, 4 squared is 16, minus 6 times 4, so minus 24 gets me a negative 8. Oh, then I have a negative 8 plus 8, which means, once again, I have a 0 in my denominator. So direct substitution did not work. Which means we're going to our next step. Let's try and see what happens when we factor. And so we already factored this in letter A, so I went ahead and copied it down. Again, canceled out the factor of x minus 2 that was in my numerator and denominator. But oh my goodness, again, there is a reason that they are asking me for the limit as x approaches 4, and that's because I see that there is like an x equals 4 type deal coming out of a factor in my denominator that's not canceling it with a factor in my numerator. And we know, again, based on what we talked about in Unit 2, way back in Try 1, that factors in my denominator that are not canceling with anything in my numerator are creating vertical asymptotes for me. And so when I go back to that graph that we have of this function, what do I notice is happening at an x value of positive 4? Exactly what I thought would be happening. Because of me being an expert PCH student, I know that there is a vertical asymptote happening there. And so I know that when there's a vertical asymptote, right, we kind of have like two options. My graph is either going to be going down forever, approaching negative infinity, or it's going to be going up, approaching positive infinity. And we need to figure out an algebraic way to figure that out. Because again, we're not going to have the graph. We're just using that to support our understanding. And so when I recognize that, hey, after direct substitution, it doesn't work, so I factor. In letter A, I recognize that once I factored, the x value that I was looking at was at a hole, and so I was able to cancel those factors out, try direct substitution again, and my life worked out for me. Vertical asymptotes are going to be a little bit different because what you notice, if you try to do the exact same thing that we did in letter A, which is direct substitution, I'm still going to have an issue. When I plug in a positive 4 for x, well, I get, 4 plus 3 in my numerator, that's fine. In my denominator, I'm going to get 4 minus 4, which still is 0. So we still have a problem. Direct substitution still does not work for us. we need to plug in some values that are really, really, really close to 4. What I mean by that is, if we think about this in terms of a number line, right? We have 4, on the left is maybe 3, 5. We want to plug in some value that is really, really close to 4, like a 4.00001 type deal. And the reason I'm looking at the right is because that's what they're asking me for, right? The limit as x approaches 4 from the right. What's happening? So I'm looking at an x value that is very, very close to 4, just to the right of it, though. And when I use direct substitution there, well, when I have the limit as x approaches 4 from the right, when I plug that in, I'm actually going to save this for a second. I'm going to get 4.0001 plus 3 all over 4.0001 minus 4. And when I evaluate that, in my numerator, I can say this is like 7-ish. It's going to be very, very close to 7, but, not exactly. In my denominator, when I evaluate this, I'm going to have a positive 0.0001. If I were to plug this into my calculator, I'm going to get a massive number, like 70 or 700,000 for my y, which is telling me, hey, this limit is approaching positive infinity because this number is so big. And we see that that is happening from the right as I am looking at my graph. As it approaches an x value of 4, it is approaching positive infinity. And so this makes sense to me. If I were to plug this into my calculator, I would see that algebraically. The nice thing, though, about recognizing the fact that this value that we're evaluating the limit at, recognizing that it's a vertical asymptote, is that we know our answer has to be either positive infinity or negative infinity. And so in a way, really all we care about is the sign of my numerator and the sign of my denominator. Well, 4 plus 3, that's obviously going to give me a positive. 4.0001 minus 4, well, that's going to give me a positive, just barely, but it's still going to be positive. A positive divided by a positive equals a positive. Boom. I know that my graph is approaching positive infinity. And that would be my limit. If I'm looking at letter C, again, I have the exact same rational function. This time I'm approaching an x value of 4 from the left. Well, based on the work we've already done, we already know that there's a vertical asymptote at x equals 4. And so, again, I'm going to come back to kind of this similar place that we started at, or left off with. I should say in letter B, the limit as x approaches 4 from the left of x plus 3 over x minus 4. Except this time, instead of plugging in a value very close to 4 but on the right, I'm going to plug in a value that's very close on the left. So maybe like 3.9999 type deal. When I do that, I have 3.9999 plus 3, which is going to give me, again, 7-ish, very close. That's going to be a positive, over 3.9999 minus 4. Well, that's going to give me a negative, barely negative, just less than 0, but still a negative. Positive divided by a negative is a negative, so this limit is negative infinity. Again, because I recognize that this value, this x value that they are trying to ask me to evaluate the limit at, is a vertical asymptote. And that's when we're going to plug in these values that are very, very close to that x value, because we can't plug in 4, and we showed that in example B. All right, and so we see that happening on our graph as well. From the left, we're approaching negative infinity, and that's what we showed algebraically as well. Let's go ahead and sum this up. So when I have a hole, which we'll talk about this more in the second half of this unit, but we call that a point discontinuity. To find the limit, we are going to factor, and then we are going to substitute. We're going to factor as much as we can. We'll find a hole when we notice that a couple of our factors, or like a factor in our numerator, is canceling with a factor in our denominator. And then we're going to substitute our value into our simplified rational function. If we have a vertical asymptote, so we factor, and we notice that even when we try to substitute that value, that x value that we're evaluating the limit at, and it doesn't work still, we're going to plug in numbers. So plug in numbers close to your x value. To determine is the limit. Ooh, that was a really ugly bracket. Sorry about that. Is it going to be positive infinity? Or is it going to be negative infinity? That's what's so important about recognizing whether, like, what's happening at that x value. Is it a hole? Is it a vertical asymptote? Is there nothing there? Like, what is happening? Because that's going to help you determine, well, if it's a vertical asymptote, I know my answer has to be positive or negative infinity. All right. What I would like for you to do now is take an attempt at these 3 practice examples that I have for you. Again, first try direct substitution, see if it works. I'm going to tell you it won't work because we're going to practice factoring and doing some things. Once you factor, see what's happening at this x value. And I want you to note that, like, hey, is it going to be a hole or is it a vertical asymptote? What is happening there based on what you know from your knowledge about earlier this year in PCH? And then do the proper steps after that, and we'll check in just a second. All right, let's talk through some of the process for these 3 examples. So for letter A, of course, the first thing I always try is direct substitution. And when I plugged in a -4 into my denominator, I ended up getting 0, and so that's why I had to take a different approach. Once direct substitution did not work for me, the next thing I needed to do was factor, and so I factored my numerator. You can see my work here in pink. I also factored my denominator until I got this limit that is down here in teal, this slightly blue color. What I notice is that at an x value of -4, that is coming from factors that are in my numerator and denominator that cancel, which means I have a hole. And that is a note I made to myself because that changes the way I approach the rest of this, evaluating this limit. And so because it's a hole, I'm going to try direct substitution again, but this time into my simplified rational function, getting rid of those factors that cancel out. And once I do that, I get a y value of +1, and that is my limit. For example B, again, the first thing I tried was direct substitution. I ended up dividing by 0, which is a no-go for me. The next thing I needed to do was factor, but in this case there was nothing to factor. And so as I'm looking at what I have already here, I noticed that what is happening at x equals 5? Well, that is coming from a factor in my denominator that is not canceling with anything in my numerator, which means that on my graph I have a vertical asymptote at x equals 5. When I have a vertical asymptote, and of course, again, I made that note for myself there, I know that my answer is either going to be positive infinity or negative infinity, and I'm going to find out which one it is by picking a number, in this case, that is just to the left, just to the left of 5, because I'm looking for the limit as x approaches 5 from the left. I picked 4.999, and because I know my answer is going to be either positive or negative infinity, when I'm plugging in 4.999, I don't need an exact answer. I just need to know, hey, when I plug it into my numerator, is it going to be positive or is it going to be negative? In this case, it's obvious. You don't even need to multiply the numbers all out. It's going to be positive. In my numerator or my denominator, it's going to be negative. And when I take a positive and divide it by a negative, I end up getting a negative. So this limit for B was negative infinity. For letter C, once again, direct substitution first did not work for me, so I needed to factor. And once I factored, I saw that at x equals 2, I had a hole because my factors were canceling there. And so I plugged into my simplified rational function and got my answer to be 5/4. Yes, it is a lot of algebra, but yes, as well, you can do it. I believe in you. I've seen you do it before, and I want to see you do it again. The calculus part of all this is very small. You know how to do all the rest, all right? Now, the last technique or thing that we might need to do in order to evaluate a limit is by rationalizing using the conjugate. And that's going to come back to our second warm-up example up here, in which we notice we have a radical in my denominator, and we don't like that. We need to get that away. We need to get it out of there. Now, normally, right, you would try and multiply by like the square root of 3 over the square root of 3, because that would help us get rid of this denominator. The radical in my denominator. But what we notice here is that there is not just a square root of 3 in the denominator of my original rational, in my original fraction. I have something being added to it, which is going to change things, right? That means we can't just multiply by the square root of 3 over the square root of 3. And like, if you wanted to prove that to yourself, you could actually multiply this out and distribute. Yes, my square root of 3 times negative square root of 3 is going to get me a negative 3, but what happens when I multiply 4 times the square root of 3? I'm still going to have a radical in my denominator, so that like doesn't do anything for me. In this case, when there's something being added or subtracted to my radical, we're going to multiply. And what I mean by conjugate is when we're looking at the denominator, we're going to keep my 4 in my square root of 3, 4 square root of 3, except instead of a negative like I see in my original fraction, I'm going to change it to a positive. I'm going to change it to a positive. And this might actually look similar to us because we did the exact same thing when we were working with imaginary numbers, when we were prepping for the SAT, right? We know that I equals the square root of negative 1. And so when we had an I in our denominator, that meant we had a square root, a radical in our denominator. We had to get it out. And so we multiplied by the conjugate. So this, might be not as fresh for some of us, but we've definitely seen it. We've definitely worked with it before. And so when I do this, the numerator I can simplify. I'm just going to keep it separate for right now. So 2 times 4 plus the square root of 3. But what I notice when I multiply my denominator together is I have 4 times 4, which is going to get me 16. When I look at my middle terms, I have 4 times positive root 3 and 4 times negative square root of 3. My middle terms are going to cancel out. The last thing I need to do is my negative square root of 3 times positive square root of 3. That's going to get me my negative 3. And we notice that in my denominator, I no longer have a radical. I just have what looks like is going to be 13. So that's the whole point of multiplying by the conjugate. Because my first sign is negative, my second sign is positive, that means my middle term is going to cancel out. And that helps us. That's our entire goal. And so, if we look down at this example in A, I know I have the graph here. We're going to ignore that for now because, again, you're not going to be given a graph on the actual AP exam or when we do a lot of this practice. We're going to have to work with this algebraically. First thing I try is direct substitution. When I plug in a negative 1 in my denominator, I end up dividing by 0, which, again, is an issue for me. And then if I go to my next step of trying to factor, well, there's nothing I can factor here. And again, when they're asking you about this value of negative 1, there's a reason. There is something that's going to be happening there. And if we take a look at the graph that I've provided for us, we do see that there is something happening at negative 1, but I can't exclusively see that right now, or explicitly see that right now. And there's nothing I can do to factor with a radical here to try and figure that out as well. And so when I see this radical, my goal is to really just try and rewrite this in a way that is going to help make apparent what is happening at an x value of -1. And so there might be a chance, like when I move this radical in my numerator, there's a chance I might end up having it in my denominator. That is fine for this case, and I'll explain why here in a second. If I multiply this by my conjugate, I'm going to have x square root of x plus 2 plus 1 over the square root of x plus 2 plus 1. And something that I notice is going to happen is I'll have the limit as x approaches -1 of, again, when I'm multiplying by the conjugate, my first term, x square root of x plus 2 times square root of x plus 2 is just going to be the x plus 2. My middle terms are going to cancel out, so I'm only needing to focus on my last terms now. -1 times +1 is -1. With my denominator, you might be looking and saying, hey, do I really need to multiply all this out? Like, that's going to be really, really complicated for me. Like, I'm telling you, this is one spot where you actually don't need to multiply it out. I actually want you to keep it separate as x plus 1 times the square root of x plus 2 plus 1. The reason for that is, just like when we were doing these examples here, when direct substitution didn't work out at first, I said, hey, direct substitution didn't work. Next, I tried factoring. When factoring worked, I went back to direct substitution. Well, we're going to do the same thing for this example that we're working on now. Direct substitution, tried that first, it did not work. Did not work. For example 3, we tried factoring. We couldn't factor. And so we moved on to step 4, which was multiplying by the conjugate to try and rationalize either the numerator or denominator. That worked, and so now we're going to go back to step 3, which was factor. Well, why would I multiply all of this together when my next step is just going to be to factor it apart again? And so by keeping it factored, we're essentially like checking that third step of factoring. And so that's why I want to keep those separate. In my numerator, I have x plus 2 minus 1. When I simplify that, I just get x plus 1. And what do I notice? I have a factor of x plus 1 in my numerator, a factor of x plus 1 in my denominator. Oh my goodness, now I see that at an x value of -1, I have a whole. And I see that on my graph, right? That's what we should have gotten. That is no surprise to me. And so now I get to go way back again to step number 1 now that we factored. And I get to do direct substitution to finish this off here. All right, and so I have the limit as x approaches -1. All that's left in my numerator is just 1 over the square root of x plus 2 plus 1. And when I do my direct substitution, I get 1 over the square root of -1 plus 2. Well, that's going to be the square root of 1, which is just 1. And so my limit is going to be 1 over 2. 1 over 2. And we can see that on my graph, the y value of my whole is 1/2, 1 over 2. And so that is evaluating limit by using multiplying by the conjugate. This is the hardest limit to try and evaluate algebraically. There's obviously a lot of work that we're doing here and a lot of algebra, but this is not going to be the most common one. You have done the hardest limit that you could evaluate in this way. And so I want you to go ahead and try example B if you're feeling up to it. I think it's really, really important we get this practice. We are going to be done now. Otherwise, I'm going to have you practice a little bit in Khan Academy before you join class just to get a few more reps before we do some together. So if you're doing letter B, I'll show my work here in a second. Otherwise, go ahead and move on to Khan Academy. All right, so I tried direct substitution. It did not work. I was dividing by 0. Then, of course, I noticed that there's not really much I can factor here at all. And so I needed to multiply by the conjugate, see if I could move this radical into a different spot. And yeah, see if that tells me what's going on in an x value of 5. And so when I multiplied by the conjugate of the denominator, the conjugate of like where my radical is, I ended up noticing that in this step down here in blue, when I left my numerator factored, right, I did not need to multiply that stuff together, and I simplified my denominator, I saw that I had a factor of x minus 5, canceling with a factor of x minus 5. And so I knew that I had a whole at an x value of 5 on this function. The part that might have been a little tricky for you was in your denominator you got negative x plus 5, which had the opposite signs of the factor in my numerator. So if I pull out like a negative 1 as a GCF, that will change the signs to positive x minus 5. And that's what you kind of see here. And so when I get rid of the factor that I canceled out, I'm left with a negative 1 in my denominator. And that is where that negative comes from. And then when I do direct substitution again, because it is a whole, that is what our next step is to do, I end up getting negative 6 for this limit. All right, folks, this was a lot. We will practice this a lot, and it's fine if you are not fully like getting it right now. Do your best to try and look over your notes, walk or go back and watch anything that you need to again, and try some practice on your own so that we can come ready with any questions we have for class. All right, I'll see you later.